Then we'll go over in the first part of the meeting a little bit of the principles of how they work so that you'll have a better idea of how to use the telescope and what its capabilities are and how to get the most out of it. And then we will go over in some detail, in general detail, how's that, of helping you set it up with some slides and pictures and general principles. And then during the break, if you brought a telescope with you, we will make sure that you can set up your telescope and get it operating. And then in the second half of the meeting, we'll go over some techniques on how to find things with the telescope, because most people will maybe find the moon and a couple of planets and then not know what to do with it and put it away in a closet or up in the attic. And we certainly don't want that to happen. First, the different types of telescopes. The refractor is the one most people think of when they think of a telescope. It's the archetypical telescope with the, where did I put my pointer? Well, that's pretty faint. Here's the one I was going to use here. Yeah, the lens up in the front end of the telescope, and you look through the back of it. Like I said, this is what people think of. Most of the early telescopes were of the refractor design. Binoculars are refractor telescopes, so are monoculars. Here are a couple of commercially available ones, and a big one. This is the 26-inch telescope, a refractor at the U.S. Naval Observatory in Washington, D.C. I have actually been to that observatory and seen that telescope and looked through it. It's on the grounds of the Vice President's house, or another way to put it is the Vice President lives on the grounds of the U.S. Naval Observatory. Question?
Can we turn off the lights?
Can you see this all right? We can turn off lights when we get into dimmer pictures, maybe. We could do that. We can even do it right now if people aren't still coming and going. Don't want anybody to fall down the stairs. Let's get some on in the very back, maybe. Let's see, was that the very back? It'd be nice if these were in some kind of order. Okay. I only taught here 34 years and never did get the idea straight on that. Yeah, so the refractors are, you know, even a pirate's telescope, I guess that'd be archetypical. Anyway, then there's the reflector telescope, which is an entirely different design. It has a mirror down at the bottom end. The light comes through the front, hits the mirror, and then either comes out the side or back through the mirror, in several different designs. But the main reason it's called a reflector is because the main light gathering component is a mirror. Here are some reflector telescopes, some small commercially available ones, some big commercially available ones, including this monster here, which is a whole lot like Jeremy's telescope. He's got a 20-inch reflector on this kind of mount, a professional observatory, and a space telescope. And here's a little bitty one that Edmund Scientific used to sell. It was called the AstroScan 2000. It had a little 4-inch mirror down on the bottom, like this bowling ball on a stand, and you could aim it around the sky with that and actually see things through it. Then there's a third type that's a hybrid of the other two called catadioptric. Notice there is an R there. It's not optic, it's optric. So that's we'll let you know, let people know that you know the different types of telescopes if you say that properly. Here's an example of one that uses a mirror to gather light like a reflector, but it also has a corrector plate in the front. So it's got, which is like a lens. So it's a combination of mirrors and things like lenses. We'll go over the details of these in just a moment. Here are several of the hybrid design telescopes, including one here right behind me. More details on the refractor telescopes. A refractor telescope is based on the principle that a lens refracts light. The light waves passing through a lens are bent by the glass as they pass through and eventually come to a focus. The term refracting is just a fancy word for bent. And the reason the light bends as it passes through the glass is because the glass slows it down. We know that light travels at 186,000 miles per second, but that's in a vacuum, and slightly slower in air and much slower going through glass or water. In fact, the glass slows down the light to maybe 2/3 or half of its normal speed as it's going through the glass. And then in one of those miraculous things that's part of modern physics, we realize that the light speeds back up again to its full speed after it comes back out of the glass. The slowing down is only while it's going through the glass. And that curving of the waves causes the light to converge to a focus. An analogy I sometimes use on this is, suppose we got everybody in the front 2 rows to hold hands and start running across the soccer field out here. Well, we'd be moving in a straight line just like one of these wave fronts. Suppose we encountered an elliptical shaped or lenticular mud patch. As we start slogging through that, the ones that are moving through the center, where it's thicker, are going to be slowed down more than the ones that just have to cut through the outer edge, and that will cause them to lag behind the others. And if you're still holding hands, we'll have a curved line now. And if we keep all running straight ahead, we'll eventually pile up in one spot, which is analogous to the focal point of the lens as the waves pass through it. At that point, an image of whatever the telescope is aimed at is formed. When I was a kid, I used to be fascinated by the fact that I could get a big magnifying glass and go into the bedroom, turn out all the lights, and hold this magnifying glass up to the window and a piece of paper back behind it and get an image upside down of the whole world outside on this piece of paper, because the image is formed by the lens there. You can't look at it directly, as we'll see, because when light rays enter your eye, they have to be just about parallel in order to be focused by the lens of your eye. So if they're converging like this, or if you let them go past the focal point where they diverge, your eye can't handle that. So we have to modify that in order to make an actual telescope. The way to do that is to put another lens after the focal point, which does the same thing with the diverging light, straightens it out into parallel rays again so that you can put it up to your eye and look through it. The image is upside down because the rays have crossed at the focal point. In astronomy, that's usually not a problem. A star looks pretty much the same right side up or upside down. And planets, you can get used to that as well. Other objects, if you used to seeing pictures of them a certain way, they will maybe appear upside down from that, but no problem. If you're using it to look through your neighbor's window, shame on you. Those images will be upside down, but we're supposed to be interested in other kinds of heavenly bodies than that. So one of the problems with refractor telescopes, especially inexpensive ones, is a single lens like this will focus the different colors of light to a different point, sort of like a rainbow. The higher energy wavelengths in the blue part of the spectrum are bent more by the glass. The lower energy waves towards the red end are bent less, and so they will come to a different focal point, all the colors in between. So if you're looking at an object through an inexpensive telescope, you may see a blue star surrounded by a red halo, or a red star surrounded by a blue halo, depending on where you are along that multiple series of focal points. If that's the case, you need to make a point to get a better telescope soon after that, because everything will look very strange to you and objects will be distorted, and the separation between points of light is not good if they're all multiple colors. It's kind of pretty and psychedelic in a way if you're into that sort of thing, but it's not good for astronomical work. The way to get around that is to use another kind of glass to make sort of a complementary lens. They can either be a little air space in between them, or usually now they're cemented together. Use two different kinds of glass, and that kind of cancels out, not perfectly, but pretty good, the effects of the chromatic aberration. A lot of telescopes now, if cost is no object, is to have a 3-element objective lens in the telescope. Now that's can set you back some money, but you get a sharper, clearer image with less color in it. That's what makes refractor telescopes more expensive than reflectors, is because you have to have 4 surfaces, or maybe 6, not only perfectly configured in themselves, but perfectly aligned with each other. So that's a lot of workmanship has to go into a refractor telescope. So, advantages of the refractor telescope and some drawbacks. One thing, once it's made, it's pretty well aligned for life. I say pretty well rather than absolutely, because we used to have one member who carried his refractor telescope around in the back bed of his pickup truck, bouncing around on country roads, and he wondered why the images weren't too sharp, but he wasn't either. So anyway, usually no alignment required. And the long length of these refractor telescopes makes them suitable for high magnification for small objects like planets and close double stars. We'll see how that works shortly on the magnification, but this is due to the long focal length of most refractor telescopes. The lenses are limited to a small diameter because, for one thing, you run out of money trying to get a big one. Another thing is glass does kind of sag under its own weight, and it's hard to support a refractor lens because it has to all be done by the edge. You can't build a framework for it in the back because the light's got to go through it. So that puts some limitations on how big the refractors are. The largest one in the world is the 40-inch refractor telescope at Yerkes Observatory at Williams Bay, Wisconsin, operated by the University of Chicago. And one I showed you is a 26-inch, and I've looked through a 30-inch telescope to see Pluto through it at the Allegheny Observatory in Pittsburgh. But it's a big deal to use a telescope that size. And we've already looked at the idea of the chromatic aberration in the refractors and relatively high cost. For some people, cost is no object apparently, but for most of us, that is a factor. The refractors are best for small, bright objects such as the moon, planets, and double stars. Now, this leads to an important point. What is the main purpose of a telescope? Most people will say it's to magnify things, but that's a second effect. The main purpose of a telescope is to gather light, more light than your eye can gather. And what you do with it, the amount of magnification you put to it, is varied according to the situation at hand as to what you're looking at. But if an object is very bright to start with, like moon and planets, you don't need a big diameter telescope to gather enough light to observe it well. So small refractors are a good telescope for looking at the moon and planets and individual stars like that. On to reflector telescopes. Type with a mirror in the back, open in the front, and a number of various things can happen with the light after it's gathered by the mirror. The basic principle is that a concave mirror will gather the incoming light and bring it to a focal point just like the lens did. My father had a shaving mirror that was a magnifying thing so he could see all his whiskers and shave them off. That apparently is not a genetic characteristic because I really didn't do that for very long. But you can also take a shaving mirror near the window and reflect the light back onto a piece of paper and get another view of the outside projected onto the piece of paper, just like with the magnifying glass. And again, we get a focal point right there. There's no chromatic aberration because all colors of light are reflected the same, unlike the refraction through a lens. The mirror actually, we just draw it curved, but the cross section of it is actually a parabola. It straightens out as you go farther and gets more curved near the center and then straightens out more out near the edges. You start out making a mirror like this, grinding it to where it's spherical. If you just grind two pieces of glass together with grit in between, the upper one will become concave and the bottom one will become convex. And that gives you a spherical curve. Then you spend 2 or 3 times that long adjusting the curve on the mirror until it becomes a parabola. And then it will bring the light to an actual point. If you have a spherical mirror, it won't do that. It's pretty easy to make large mirrors. For one thing, you've only got one surface to figure instead of 4 or 6 as we would have in a refractor telescope. And it doesn't even have to be perfectly transparent. It can have bubbles in it. It can be a honeycomb shape to make it lighter. Some of them were even made out of a ceramic material that wasn't even transparent. And also you can support it from the back so it doesn't sag because the light doesn't go through the mirror. Now, let me just back up for a second here. Let's see how far back I want to go here. Well, now let's just go to the picture of it here. This diagram, instead of going back to if this telescope is like the Mount Palomar telescope and the mirror is 17 feet in diameter, you can climb in here and observe at that point. Set up a photographic plate or even use test eyepieces and things in a little cage that's right at that point. Now, if your telescope is this size, that isn't going to work. So you have to use an alternate plan, and that would be to put in a small diagonal mirror at this point to send the light out to the side. And then you can observe through the side of the telescope without your head blocking the incoming light. This is Isaac Newton's design. It's what we still call it, a Newtonian telescope. And the eyepiece goes in the side just as it would on the bottom end of a refractor telescope. Now, when you're observing through a reflector telescope, you're looking at right angles to the direction the telescope is aimed. That makes it hard to aim the telescope unless you have a finder telescope attached to the side, sort of like the sighting scope on a rifle, where you can look through that at what you're aiming at and then come around and look through the eyepiece of the telescope to get the magnified view. So you really do need a finder telescope, preferably one with a straight through design. Some people have one that has a right angle observing eyepiece on the finder. Then you're back to the same problem again, and you need a finder for the finder so that you can have something to sight along and aim at the right spot in the sky. It kind of reminds me of Belloc's poem about fleas. Y'all know that one? Large fleas have smaller fleas upon their backs to bite them. These smaller fleas have lesser fleas, and so on ad infinitum. So you have the right angle telescope, and then if you have a right angle finder, you need a smaller finder to finally aim it straight. Here's a straight through finder scope. This is not being put up as an example of a good one. This is the one that used to be on this telescope. We took it off and threw it away because it was a 1-inch diameter, but it was a plastic lens, and it was stopped down because the chromatic aberration was so bad it was really only wound up being about a 1/2 inch in diameter, and the mount was plastic and kind of flexible, and you don't want a flexible mount on anything dealing with a telescope. So here's one that you can buy, but we went and bought a nice one that's, I see the dovetail base is still on there. The finder is somewhere, I hope, Freddie. You're pointing at something.
It's in the box.
Oh.
The box that
Well, yeah, okay. Yeah, in here, we can see it at the break, I guess, is a very nice finder scope that we bought to put on this so that it can be used a lot more easily. Here's one of the famous right angle scopes, and as you can see, it's probably easier on your neck to look through, but that doesn't do you a lot of good if you can't find anything with it. So. And then we come to the red dot finder. I meant to leave off the word scope there because it's not really a telescope. It doesn't have any optics in it. It just has a little slanting screen inside, and a red LED or laser or something shines at the center of it and puts a dot, and so when you look through this tube, you see a dot projected against the sky. And theoretically, that helps you aim the telescope. Well, it's better than nothing, but it doesn't have any light gathering power. It's just the same as your eye, except less, because the little screen that's in there cuts out some of the light that you'd normally see. You'd be better off just taping a toilet paper tube to the side of the telescope and looking through that as the red dot finder. So if you have one of those, you can take it off and either throw it away or give it to somebody who has a right angle finder and needs another finder to find with the finder. Advantages and drawbacks of reflector telescopes. Well, they do need to be aligned. They all have screws to adjust the mirrors in them, and from time to time they need tweaking. Now, if you take care of it carefully and put it on the back seat of your car rather than in the trunk, where it doesn't get bounced around as much, it'll stay for a long time before it needs realignment. It's very easy to tell when it needs aligning. One is stars don't come to a sharp focus, but start out as points on one side with the tail going off to the other side, and then as you focus it, the tail switches over to the other side. So you know something is wrong. Also, it's easy to tell just looking down the tube of the telescope and through the eyepiece holder exactly what's wrong and what needs to be fixed. And when you get good at it, it only takes a few minutes to line it up. The first time, you may think it's a very long, complicated procedure, but it's not that much trouble. Eventually, the mirror needs resurfacing because remember the reflective coating is on the surface of the mirror, not the back like in a mirror in your bathroom. It's right there on the surface, and it can get damaged if it gets dirty or scraped or if you try to clean it the wrong way. The best way to clean it is to not let it get dirty in the first place, but if you do, there are ways to do it, and we have all of these in our handouts and online. The resurfacing, it all depends on how well it's coated. This telescope, I bought this in 1957, and I'm still on the first coating, so it's very likely to outlast me in this original coating. So if the coating is not good, it may need resurfacing, but a lot of times they'll last a good long time. Low cost per inch of aperture. You can get a good size reflector for about the same amount of money as a rather small refractor because of the less work involved in building it. And it's easy to make large diameters. The best diameter is the biggest one that you can afford and can carry around, because you can make one and buy one for a reasonable amount of money that's bigger than you can carry. So you need to keep that in mind when you're selecting a telescope. These are best for objects that are dim, such as a nebula or dimly glowing gas cloud in space, or distant galaxies, little fuzzy smudges that you have to know are galaxies before you can even see the spiral structure in them, like little miniature Milky Way. That makes up for the fact that the mirror is spherical instead of parabolic, and the light will come to a focus. And with the corrector plate there, most of these are arranged that have a convex secondary mirror aimed straight back through a hole in the mirror. So on this telescope, you can see, let me turn it just a little bit here.
It's an orange thing in the middle. Yeah.
Okay, that locks it in place.
Yeah.
Well, okay, the mirror is inside here, the corrector plate is up in the front, and the secondary mirror is on a little spot right on the inside of the corrector plate, and it's got a convex curve to it that reflects the light back through a hole in the mirror. So at the break you can come up and see the adjustment here for the secondary mirror. This gives you a long focal length. And a lot of people think that's because the light goes back and forth through the telescope several times that gives it the long focal length. The long focal length actually comes from the convex curve on the secondary. You can see that the light here would be coming to a point of focus right about there. You follow that arrow down to there, this one to here. That's about where the focal point would be. But with the convex secondary, that slows the light cone down and makes it extend further. So when you're here at the eyepiece, this makes it look like a much longer telescope, that it's really, the front end is way out here. So that's why it has a long effective focal length, is because of that convex secondary. Advantages: it's good for all kinds of observing. Galaxies, nebulae, moon, planets, individual stars, with various adaptive optics inside, with things that make the field bigger or smaller, higher or lower power. You can do observing of all types of objects with that. It seldom needs alignment, which is good because you can't get to the primary mirror. It's pretty much sealed up inside. The only thing you can adjust is the secondary mirror, which usually has 3 little screws on it. And if you do have one of these and it does get out of alignment, you'll see the usual symptoms are the stars don't come to a sharp focus. And there's a simple way to adjust the secondary mirror. I suggest, though, that if you go to do that, you buy some little knurled knobs. There's a place that sells them. It's called, I think it's Bob's Nuts or something like that. Bob's Knobs or whatever it is. Okay, whatever. And it's a lot easier to work with those in the dark than to come out your corrector plate with a screwdriver or an Allen wrench in the dark. So I recommend that you get those. The convenience you pay for. These are much more expensive than a regular reflector. Not as bad as a refractor that size, but they do set you back quite a bit. Some of them, you can actually get bad ones where they don't ever focus no matter what you do. So stick with one of the main good brands of their high-end scopes. Nothing suspiciously low priced. Don't get those. Get the main ones like Meade or Celestron. Another problem in this part of the country is you got this piece of glass right on the front end of the telescope, and dew will settle on it in this part of the country quite frequently. Now there are ways around that. They will sell you little extenders that make the tube come out farther so it's recessed a little bit, and heaters that wrap around it so the dew doesn't settle on the corrector plate. Okay, so those are the 3 basic types of telescopes. A refractor, like we have down here, a couple of reflectors, and the hybrid catadioptric scope here. What I'm going to show you now are various principles of telescopes that apply to all types, not just any one of those. First is the concept of magnification or power. When a beginner is buying a telescope, that's the main thing they're interested in, is what's the magnification or power of the telescope. And if you buy one, your neighbor will ask you, what power is it? Well, that's a whole lot like asking, how fast will your car go? It's adjustable. And the telescope power or magnification is adjustable. And to further the analogy, you probably don't want to know what is the maximum speed of your car before it falls apart. And using a telescope, you very seldom use the highest possible power. Most of the time you'll be cruising at a much more moderate magnification. But it's a selling point. If you go to a department store and buy one, that's the biggest thing on the box, 600X or something like that. I get calls all the time from people who've gotten one, and they can't tell me whether it's a refractor or a reflector or what brand it is or how big it is or anything, but they know it's 600X. So I figure, well, we got our work cut out for us when we show them how to use it, because that's the main thing you don't want to fool with. The power of the telescope is a simple ratio of the focal length of the objective, which could be the lens in the front of a refractor or the mirror in the back of a telescope, divided by the focal length of the eyepiece. The eyepiece is how you adjust the power of the telescope. Got a number of eyepieces here. Here's a relatively long one, 28 millimeters focal length. Here's one that's 12 and a half, this one's 18 millimeters. And here's one that's 12 and a half millimeters. And these different focal length eyepieces give you different magnifications as you slip them in and out of the eyepiece holder of the telescope. Most people are interested in putting in the highest power eyepiece first and looking with that. If you've ever taken biology in high school, a teacher probably told you, find things with the lowest power and then switch to one of the higher power objectives. That's true with the telescope as well. If you try to find things with a high power, the field is so narrow that you're almost doomed to failure to try to find anything at a high power. Now, why does that give you the power of the telescope? Well, the magnification is really the ratio of the diameter of this bundle of light rays compared to this bundle of light rays. When you look through the telescope with your eye here, the lenses trick you into thinking you're seeing something that size instead of that size. So that ratio is the power of the telescope. But if you notice, these are similar triangles here. The size of this lens, the diameter compared to its focal length, is the same, or rather the size of this lens compared to that lens is the same as this focal length compared to that focal length. So if we set up the ratio of the diameters, that's the same as the ratio of the focal lengths, which is easier to measure and doesn't change when you stop something down. It's all remains the same. So the power formula is focal length of the objective divided by the focal length of whatever eyepiece you have in there at the time. So the shorter the focal length of the eyepiece, the higher the power for a given objective in the telescope. So obviously, this lens will give you a higher magnification than this one. Here's an example. A telescope has a 48-inch focal length, like this one. And if we put in a half-inch eyepiece here, that will give us 96 power for that particular setup. If we put in the one that's 28 millimeters, about 1 1/8 inches, that gives me about 42 power for the low end of the thing. Nowhere near 600, by the way. You never need anything like that. We'll see in just a moment that there's a maximum useful power as well, like right here. The practical limit is about 50 power per inch of diameter, whether you've got a reflector or a refractor, 50 power per inch. You'd have to have a really big telescope to get up to 600 power using that rate. Here's an example. A 2 1/4 inch refractor, standard department store size, gives a maximum useful power of 2 1/4 times 50, or 113 power. Nowhere near the 600. The reason for that is you only have a certain amount of light to work with. The image that's sitting there floating at the focal point of the lens is what it is. It depends on the gathering power of the objective lens or mirror of the telescope. You can look at it with more powerful and more strong eyepieces, but all you're doing is blowing up the same amount of light to a bigger size, and you're not going to see any more. It will look bigger, but eventually goes away. You know, like this projector here, how could we make this picture bigger? Well, we could move it farther back, couldn't we? What if we put it over on the other side of Central Avenue and project it up against the side of the building, assume we could focus? It would be huge, but you probably couldn't see it because we still got the same amount of light, but it's spread out over such a big area that there's nothing you can see. So the secret to high magnification is to get a big enough lens that will gather enough light to support higher magnifications. If you try to put too much power on a small telescope, you'll be terribly disappointed. So this is one of the main things you need to remember when you're getting started, is to always use the lowest power eyepiece, and then if it really looks small and is plenty bright, then put in a shorter eyepiece, which gives you a little higher power, and work your way up from there. And you'll find that you almost never use the highest possible magnification. It's usually more useful and more satisfying. It gets bigger with higher power, but not necessarily better. Everything that's in the image is there when it's small as is when it's big. Okay, limiting magnitude. Now this may be some terms here that some of you aren't familiar with yet. Magnitude is the term we use for the brightness of stars. The brightest ones in the sky are known as first magnitude. And the dimmest ones we can see with the naked eye under really good conditions are sixth magnitude. Certain things, like some of the brighter planets like Venus, I'm sure you saw Venus this evening out in the west, that's about magnitude minus 4.3 now. It's so bright that it goes negative on the magnitude scale. So a telescope of a particular size will let you see stars down to a certain magnitude. And if the object that you're looking for is fainter than that, you won't be able to see it. No matter how much you cross your fingers and wish upon a falling star and everything else, you're not going to see it. Here's the formula. The magnitude of a telescope, limiting magnitude, is 9 plus 5 times the log of the aperture, and that's in inches. Now, everybody's calculator has a log key on it, but most people don't know what to use it for, and even fewer know what it actually means mathematically. It's one of those things that's gone by the wayside, like Latin and other things. Anyway, the key is still there, and you don't have to know what it means to use it. You put in the aperture of the telescope in inches, hit the log button, times 5 plus 9, and that will give you the limiting magnitude of your scope. For a 4-inch telescope, the log of 4 is 0.602. We used to have to memorize all of those. And 5 times that is 3, plus 9 is 12. So a 4-inch telescope will let you see 12th magnitude stars, whereas your naked eye only lets you see down to 6th. And how do you know how bright the object is? Well, whatever source you're using, a manual or star chart or something, will tell you how bright the object is, so you'll know whether or not it's within the range of your telescope. And then you also have to take into account the lighting conditions. You know, if you're in a neighborhood that has a lot of lighting, you're not going to be able to see as much as if you're out at our dark observing site. Something that may tie to your knowledge of cameras. If you don't know anything about cameras, this won't make much sense, but we'll just pass over it quickly. The speed of a telescope's optics. Divide the focal length by the aperture or diameter. So a 6-inch telescope with a 48-inch focal length, 48 divided by 6 is f8. This telescope is an 8-inch with 48-inch focal length, so it's f what? 6. Very good. So f6. So it's a little faster than the f8. This one is f11. It's 48-inch focal length with a 4 1/4-inch mirror, which works out to about 11.3. So it's a very slow telescope. The smaller the f number, the lower the magnification, the wider the field of view, and the brighter the image, all else being equal. Those of you with camera knowledge know that. If you have a lens on the camera that when it's wide open it's f1.4, if you stop it down to f16, the image is not going to be as bright. Same deal. The ones that are faster are generally better for wide field viewing of dim objects like galaxies and nebulae. The slow ones are good for high power, things like moon, planets, double stars, so on. And the ones in between, f6 to f10, are pretty much middle of the road, will work either way. Now we get to the mountings of the telescopes, which is extremely important. Most people don't think much about a mounting when they're buying a telescope. But using a car analogy again, if you had a snazzy sports car with a really powerful engine, but the tires fell off every time you took it out, you wouldn't take it out very much. And that's what happens if you've got a pretty good telescope, but the mounting is shaky and flimsy. It won't let you do any observing, and you'll put the telescope away. There are two basic types of telescope mountings, alt-azimuth and equatorial. Each one of those is subdivided at least two ways. I've kind of combined things here a little bit, but there are two main ways to subdivide each one. If we look at the alt-azimuth mounting, the alt part means up and down. The azimuth part means the horizontal sweep around the horizon. So up and down, back and forth. Here are some telescopes with alt-azimuth mounts. Here's one that you can see right there. There's a pivot point that lets the telescope aim higher and lower. There's another pivot point right at the top of the tripod that lets it aim right and left. Here's one that's a lot better made, but it's still an alt-azimuth mount. Here's the axis that it can turn around on horizontally, and then here, pivoting the telescope in between, is your vertical motion. This type of mounting that we'll see a little more about, the Dobsonian mounting that this Orion telescope is on, has this part right on the ground. And then the up and down motion is achieved through that pivot there, but the whole thing is on like a Lazy Susan turntable at the bottom that lets you aim in all different directions. The standard alt-azimuth mount, as opposed to the Dobsonian, you can see has a pivot motion there that lets you aim higher and lower, and then around the top here we can aim in all different directions. This one is a little fancier because it has a knob that lets you have a little finer control over the motions rather than just jerking it around from one spot to another, but it's still alt-azimuth, up, down, and back and forth. The Dobsonian version of the mount lets you go up and down with it this way, higher and lower, and then to aim in different directions we turn it around this way. Those of you in the front row can see the little red arrows there as I'm turning it around. You see them? Yep. I've stopped. They go away when I stop. Okay, now these are simple to use, but they're not the best for astronomical use, since when you go to track an object across the sky due to the Earth's rotation, everything moves. That's the first thing you know. You aim a telescope at something and you get somebody to come look at it. It isn't there anymore. It's moved. And you say, it's moved. Well, actually, we've moved because the Earth keeps rotating. And whatever magnification you've got the telescope set at, like 100 power, that makes the motion of the Earth magnified by 100 times too. So things move out of the field very quickly, and you have to track them across the sky. And things don't move straight across the sky. Here's a picture of what you would get if you aimed a camera straight north near the North Star and left the lens open for several hours in a good dark place where you wouldn't get a lot of light pollution. The stars are moving in this circular path around the North Star because, that's right over the North Pole of the Earth. That's the pivot point of the sky. And every star and planet in the sky moves around that in a circle. So if you're aiming at something over here, you're going to have to move up and to the right in a curve. So a telescope that just goes up and down and back and forth isn't going to follow that very easily. Even if you're looking near the celestial equator, the point where it intersects the horizon pretty much straight east, the lines are straight here. The stars are moving in a straight line upwards towards the right, but you're still going to have to go up some, right some, up some, right some in order to follow the star. Does anybody recognize what this is, this area right here? No? Yeah. Yeah. Look at the ends of them right here, 3 stars in a row. That's Orion's belt. Just ignore the rest of it. Just look at one end of them. And there's Betelgeuse and Rigel, and there's the Orion Nebula through there. So this is Orion up a little ways, and Orion's belt points to Sirius, which would be about here at the end of the line there. So that's the brightest star. So that's what we're looking at in that picture.
I just got lucky. I saw an extremely bright streak and I said Sirius.
Well, it could have been a planet. Yes, but you were lucky, yes. Yeah. Okay. And sometimes with an altazimuth mount, it's harder to find objects in the first place. We're not talking about the moon here, but if you see that there's a star cluster directly south of a bright star, and you're aimed at that star, which way is south? It's some combination of up and down and back and forth, and that combination is a little tricky to do on your own. Now, having said all of that, some of our most successful members use altazimuth mounted telescopes and have found things quite successfully. I don't see Earl Griffin tonight, but he's can find practically anything with his 8-inch Dobsonian telescope. And Grace, at various observing sessions, she has no trouble finding things. And Jeremy's 20-inch telescope is altazimuth mounted, Dobsonian, and he's on the verge of finding all of the deep sky objects in the Messier catalog with it. So I can't say that this isn't any good. I'm just saying it's harder to use the altazimuth mount than the equatorial. So there's your examples of using the altazimuth successfully. The main thing is, whatever you use, it's got to be sturdy or it's no good. Now we switch to the equatorial mountings, and some of you may have those with a telescope, some may have the altazimuth type. The equatorial telescope has 2 axles at right angles to each other. Now that's true on this one, but I don't think all of you can see it. But this one over here does as well. You can see that here's one big axle aimed this way. This is called the declination axis, and it lets you move north and south. The telescope sweeps back and forth across that. And notice there's another, it's so huge here it's almost hard to tell it's an axle, but through this direction is the polar axis. This would be aimed straight north towards the North Star, and as the stars move across the sky, you just turn around that axis. I can show you how this one moves, but you probably can't see the mount itself working. But we do have some pictures. And it's easy to find things because a star chart will show, say, the star cluster straight south of a star. You aim to the bright star and you move straight south, turning on that axis. No zigzagging back and forth, and you'll run right across it. And tracking, once you find an object, just follow it across the sky, turning on one axis. No combination of zigzagging back and forth. There are 2 types, generally, of equatorial mountings. The German equatorial and the fork on the wedge. The German equatorial is like this one and this one. Here's the polar axis that you aim at the North Star and the sky rotates around, and the declination axis, which lets you move north and south and select different objects. Here's a slightly different design over here, but you can see the polar axis, the declination axis. Some of you have them like that. Now the fork mount on an equatorial wedge is kind of an interesting invention. I thought we were going to have one of those on display here, but I think you can tell from the pictures. Here's a fork mount that's not on an equatorial wedge. It's just sitting there. So this is an altazimuth mount, isn't it? You can go up and down with the telescope supported in the middle like that, and you can go round and round, left and right, up, back and forth, pivoted around there. In other words, you've got 2 axes at right angles to each other already. It's just that one of them is aimed straight up. Well, suppose you tilted the telescope where instead of aimed straight up, this axis is aimed to the North Star. That's what this wedge-shaped adapter does, is between the tripod and the base of the telescope, you mount this, you set it for your latitude, and you adjust this to where instead of aimed straight up, this is now aimed at the North Star. So now you've got an equatorial mount where you used to have an altazimuth mount. So that's how that works. The last part is the go-to mountings. This is where you don't worry about finding things because you have a computer that does it for you. Meade and Celestron have various versions of this. Almost everybody does, but theirs are reasonably good. They're basically handheld computers that look kind of like a television remote, but they're actually computers that contain a database of where every object is in the sky that you might be interested in looking at, and you punch in the buttons and it will turn to the object you're looking at. Now there's there's a typical one right there. It may even be the same as this one. It certainly looks like it. The reason a lot of people do this is because it saves the whole step of learning anything about the sky. You can just go out and punch in some buttons, and there the thing does appear in the eyepiece. That's one way of doing things. I'm not disparaging that way, but it's not finding things. It's sort of like if you go fishing and you bait a hook and you throw it out there and you get a bite and you pull it in, you have caught the fish, and you can tell somebody that's what you did. You could throw a stick of dynamite in the water and just gather up all the fish bodies, and that's another way to do it. Or you can go to the fish market and buy some. Any of those ways will give you fish on the table, but only one of them is the way that you would say you caught the fish and you went fishing. So if you're going hunting for astronomical objects, most people prefer to do that on their own. A lot of times, a lot of the cost of a telescope goes into this, so you're paying more for this little thing than you are for the optics and the mounting of the telescope. And whatever goes into that computer is coming out of somewhere, and that's parts that are, I think, more important. But if that's what you've got, then you need to learn how to use it. In my experience, it generally takes people a long time to get those set up when they go out observing. That everybody will be observing for a half hour of things and getting ready to pack up, and they're still trying to teach it where the three bright stars are and which way is north and where they are and all of that. And for me, when I go out observing at night, the last thing I want to do is to fool around with the computer again after doing that all day. I want to be as far away from anything like that as possible. So after you enter all this stuff into the computer and your alignment procedure, you're ready to find any object that's in the database, theoretically. Okay, setting up the telescope. Now we get into some specific things on how to set it up, and remember, we're going to go over this with you out in the lobby there during the break where you can set them up, and we'll make sure you know how to set up your telescope. It almost goes without saying, but all of these things have come from experience when somebody didn't do it that way. You set up the tripod or the pedestal that it's on first, and you make sure that everything is tight and that it doesn't wobble. If it wobbles just sitting there by itself, you know it's going to wobble with the telescope on it. So make sure that the mounting is in good shape first. If you have a German equatorial, the kind with the counterweight, be sure you put the counterweight on first before you put the telescope on. Otherwise, it'll fall over and damage itself. Then you put the telescope on its mounting and secure it to the base with whatever means it's provided. Sometimes that screws right into it. Sometimes there's straps. There are any number of ways to attach the telescope to the base. Many people that have tripods have adjustable length on them. So you can either leave it close to the ground, in which case it's more sturdy, or you can extend the legs on the tripod, in which case it may be easier to look through, but then it gets not quite as sturdy and a little more flimsy and flexible. So it's a trade-off like most things. Adjust it to where you can see through it, but it's not wobbling around. If you have an alt-azimuth mounting, there are very few adjustments you can make. So it's very simple to set up. If you have locking knobs that limit the ease of motion and the up and down and back and forth, try to adjust those to where it's fairly easy to aim it around the sky, but when you let go, it stays put. because if you're trying to aim at something and then you go around to look through the eyepiece and it's all flopped down, you haven't found it anymore. So make sure that it stays put when you let go of it. Some of them can be balanced, others is pretty hard to do. On the equatorial mounting, you've got to align the polar axis with the North Star. Now you can do this with or without the telescope on the mount. You can just set it down as you're setting up the telescope. You might take the tripod out of the trunk, set it down on the ground, and roughly aim the polar axis towards the North Star. Unless you're doing photography, that's generally accurate enough to do regular observing. Then, once you do that, you have to adjust the latitude. Now, unless you take a lot of trips, you only have to do that once and lock it in place. The latitude adjustment is the angle at which the polar axis is above the horizontal. And there's usually a scale there that lets you adjust it. You can see a close-up there. Here it's 35 degrees. That's how high the North Star is above the horizon. If you don't have one of those scales, just if you can take the some of them, like this nice refractor over here, have a little telescope built into the base, and you can look through that and see the North Star through it, including a little scale as to exactly where you're supposed to aim. Others, you can just slip the polar axis out of its housing and look through the empty housing and see if you can see the North Star through there, and move it around to where you can see it, and then that's aimed pretty much straight north when you do that. All kinds of ways to do that. But if you have an equatorial mounting, you've got to do this, or there's no purpose in having the equatorial mounting. There's no real point in leveling the mounting. A lot of them have levels built into them. Now, if you've got it adjusted to where you're automatically aimed at 35 degrees on a flat surface, then you either have to find another flat surface or adjust the tripod legs until the little bubble tells you it's the same level that it was when you set it up. But if you can adjust the latitude while you're in the field, it doesn't make any difference. I mean, you can have it mounted into the side of a hill and it doesn't make any difference. So aim it to the North Star, as we talked about earlier. Then turn it to where the telescope is aimed horizontally. I'll see if I can get this where I'm not bumping into various telescopes, along the declination axis like this. And you should be able to move it and let go of it with it staying put. It should be balanced close enough to do that. Now, if you put in heavier eyepieces or cameras or something, you'll either have to slide the telescope along to make up for that, or hang counterweights off the end to balance that. But you want to get it balanced as close as possible this way so you can let go of it and it stays put. Then you turn it the other way. Let's see, we already did that. Then we want to make sure that it's balanced around the polar axis as well, where when you let go of it, it stays put. So it's balanced around both axes, and then you do that by adjusting the counterweight. And this ought to be capitalized, bold, and underlined. Fasten the counterweight securely. If you don't, two things will happen. It will fall off in the dark and break your toe, and then the telescope will fall over and break itself. So some have a little flange on the end of the shaft there where it can't fall off, but if it doesn't, be very careful to tighten that counterweight securely. Then always adjust the knobs to where it's a little easier to move it around the polar axis than it is north and south. That way, when you're tracking an object, you can pull it along and it will follow the object. Notice the path that it's taking. Remember the picture I showed you of the stars rising in the east like Orion coming up at an angle? It comes up at an angle just exactly the right way because it's set for 35 degrees. Remember how in the northern part of the sky it tended to move in a circle? There's the circle that it's sweeping out. It follows just wherever the star is in the sky, moving it around the polar axis will follow it automatically with the equatorial mount. Okay, I already said that. Okay, finally, the finder scope. Here's the finder scope on this telescope. It's got two sets of adjusting knobs. Most of them nowadays don't. They have a rubber O-ring or something in the front that holds it securely but flexibly, and then two or maybe three. The easiest is if you've got two that are right angles to each other. This is an old-fashioned one with 320 degrees apart. But either way, you've got to line up the finder with the telescope or it's no good. If it's aimed in a different place than the telescope, it won't do you any good. You can do most of this during the daytime. Just go out where you can see a distant treetop or chimney top or a radio tower and aim at that. Get it into the telescope field of view with a low power somehow. Then you be using your lowest power eyepiece to do that. Lock it in position and then adjust the finder where it's on the crosshairs in the finder. And that will make sure that it's aimed pretty much the same way. Now it's not exactly aimed until you do it with a star. So after you do it in the daytime on some relatively nearby object, try it with higher and higher magnification eyepieces until the chimney top or light on the top of a radio tower will come back and be in the eyepiece when you get it centered in the finder. If your finder flops around, like if it's only got 3 screws in the back but nothing holding it in the front, it's not going to work. You're going to have to fill it in with something. Get an O-ring or wrap it with tape or do something to hold the front end still, because if it moves around, it's not going to do you any good and you'll just get mad at the whole thing and give up. So that's one of the most frustrating things, is to have a finder that isn't lined up and can't be lined up without moving around. And when you do that, you can either like this scope has, you can take it off and make sure that it has a little dovetail shoe that it fits into, so it will be aligned the next time you put it on. Or what I do on mine is put it on a cushion on the back seat of the car so it doesn't have any weird stresses on it, so it's always lined up and ready to go. Then you do it at night with a bright star, and then with a shorter high power eyepiece, and then you're set to go. And the more time you spend doing that, the happier you will be and the less time you will waste at observing sessions trying to find things. Okay, more first is observe misaligned finders, that and setting up computers, but one or the other will do it. If you have a right angle finder, replace it with a straight through finder, and if you have a red dot finder, replace it with one that's got actual lenses and optics in it. Okay, so that's the end of the first part, which is the longer part by far. During the break, I don't know, Rick, you want to announce this, or let me just tell them?
Go ahead.
Okay, if you brought a telescope with you, take it out to the lobby out here and have it ready to set up, and we'll help you with whatever. I mean, take it as far as you can and we'll take over from there and make sure you can get it set up to the point where we wound up here. Then after the break, after 15 or 20 minutes or however long that takes, we'll reconvene and go through some methods of how to actually find things with your telescope so that you'll actually use it. So that's it for the first half. Oh yeah, cookies, yes. Okay.